Progress.
Let's wait for a few more minutes. We have more people joining. Hello, everyone. I hope you all had a chance to at least just glance through the papers that I sent you in the WhatsApp group. Um, Before we start the presentation, let's discuss something which is even more important than discussing this paper. The question is, why should the doctors do research? It's something I'm not sure, but many of mm, our doctor friends might be wondering about why should even the doctors, not just the scientists, but the doctors should also do research. The reason is people who are scientists but not doctors, they cannot work on human samples. That's the only reason why doctors should do research. Doctors, they are authorized to work with, directly interact with people and obtain their data. They can analyze the data and they can they discover new things, which is otherwise impossible for classical scientists to discover, which is why we have Nobel Prize in Physiology and Medicine. The Nobel Prize in Physiology, that is reserved for medical finding. Now, those medical findings is only possible by people in the medical field who have access to human patients. And now let's compare doctors who do research and then scientists who do research. People who are scientists, they are traditionally trained in very science of very high rigor, because that is all they do. But the doctors, they primarily focus on patients. They are involved in obtaining patient data. And as you know, human body is way more complex than any model organism like mouse, rat, rabbit. Like, for example, all those antibodies are developed in mouse, rat, rabbit primarily. And then you have monkeys, you have guinea pigs, you have the varieties of other organisms which scientists classically work on to make their discoveries, which are definitely important to all, both animals and also humans, because humans also have the same set of genes and proteins as animals. But as you can imagine, human body is way more complex. Human body is way more complex, which is why humans have diseases that animals do not. Like, for example, right now, no one knows if mouse or rat, they have Parkinson's disease. Just a simple example. So you can imagine, given the complexity of the human body, we have so many different, like even let's take the case of COVID-19. The mouse rat didn't get COVID-19, only humans did. So that can tell you why it is necessary to focus solely on humans from another perspective, from the perspective of doctors, because they direct interact with patients. They know what's going on with the patient, what sort of problems they mostly go through. Now, in my experience, doctors who are not involved in research, it might not be true for all the doctors, but people who are not doing research, who are not making discoveries, then all they are doing is basically just memorizing a bunch of stuff and then using it to patients. Uh, and people definitely should go beyond that and make their own discoveries, which will be useful and helpful to both doctors and scientists across the world. Now that we have discussed very vaguely why doctors should very actively be involved in research, now let's discuss this paper that came out in Lancet, sister journal, basically this month. We are pretty much a combination of a pool of some 20-25 doctors came together and then did this study. And the study is a classification of Alzheimer's disease and frontotemporal lobar dementia. This is called FTD, using routine clinical and cognitive measures across multicentric underrepresented samples. A cross-sectional observational study. What's a cross-sectional study? It basically means, as you know, people in, like, let's say, India, they are different from people in, like, let's say, UK or the US. People from India, they are different, both, if you go into protein level, if you go into like in any detailed level, they're all different. They are affected differentially in different diseases. People in India are prone to lesser disease 1, but people in the US are prone to disease number 2. So, but that does not mean you don't have disease 1 in US. So when you study a specific disease, like let's say across multiple countries, where they all have different propensity to the disease. It's called a cross-sectional study. Now, in this study, basically samples were collected from 5 different countries, 11 different centers from 5 different countries, and we basically had let's say people from 9 countries involved in research. Why? Because collaboration. Now, this is the power of collaboration. And let's say people who are collecting data from patients, we are not best in everything. Someone who is an expert in physics might not know everything about biology. Someone who is expert in biology might not know everything about statistics. Someone who knows everything about statistics might not know everything about the medical field, which is why people from different background basically banded together to figure out a computer programming method to differentiate Alzheimer's disease and from another disease that basically looks like Alzheimer's disease. So we had basically statistician and mathematician, they all programming expert. They basically all came together and then collaborated with people from this Latin American countries, 5 Latin American countries, who were involved in primarily in collecting data, and then they made this discovery. This is also why people collaborate, because we are not expert in everything. We sometimes need help from people from different background, and then borrow their knowledge and their expertise to have substantial discoveries. Now, this definitely, as you can imagine, this entire paper is about brain disease, both Alzheimer's disease and frontotemporal lobar dementia. They are sort of brain disease where we have where the cognitive functions are affected. Now, this is a very cartoony figures that I found in the internet. But of course, brain is way more complex than what you see here. We have now the frontal lobe. This is also called the prefrontal cortex. And then we have the parietal lobe, and we have the temporal lobe, and we have the occipital lobe. And then this is the cerebellum. This is called the brain stem. So there's prefrontal, I will not go into details about the anatomy of the brain because that is not the main goal of this today's presentation. But all you have to know is this entire cortex, they sort of act as, how should I put it, as a helmet to protect all the organs, components that are inside the brain, which are basically components of the limbic system, which includes hippocampus, amygdala, thalamus, hypothalamus, midbrain, basically everything. But if you look at this helmet, we have frontal lobe, and we have the parietal lobe. Here we have the temporal lobe, and we have the occipital lobe. But if you don't know, you have to know this occipital lobe is very critical in vision. The frontal lobe, we have reasoning, behavior, memory, intelligence, all those things that are basically important to us. And then in the temporal lobe, we have speech, behavior, hearing, our secondary requirement. Well, everything is primary, but sure. Okay, now let's go to why, there was a need to sort of classify Alzheimer's disease and frontotemporal dementia. First of all, they are both brain disease. And second of all, as the name suggests, frontotemporal dementia is where we have the frontal lobe and the temporal lobe is affected. This is the frontal lobe and this is the temporal lobe is affected. And as you can imagine, since these regions are not affected, this is how a human brain should look like. This is a healthy human brain. It's a cross section. And then you can see you have serious atrophy in the frontal lobe and the temporal lobe. In the Alzheimer's disease, pretty much the entire brain is affected. The entire brain shrinks. The volume of the brain shrinks by 80%, like in an extreme case. In the brain, you have both, you can see, you see two different color. One looks whitish, one looks sort of darkish. This is called the gray matter, and this is called the white matter. The white matter has majority of the immune cells, and the gray matter has your neurons. And the neurons, they basically sort of die. And when you have brain atrophy, like Alzheimer's disease and also FTD. So different regions are affected. Now in FTD, you have fewer regions affected. In AD, you have a lot of regions affected, including limbic region. Like in Alzheimer's disease, you have hippocampus affected, amygdala affected, everything is affected in Alzheimer's disease. Okay, sort of let's go into a little more details. And this is basically just to show you why research in the medical field is important. You have Alzheimer's disease, you have frontotemporal dementia, and there is one more disease called DLBD. It's called dementia with Lewy bodies. Now remember, everything is dementia. In each of the cases, people forget things, but they're all coming from very different reasons. Now, I mean, all this dementia, when sort of your neurons start dying, uh, well, to be honest, no one knows why, what basically initiates these diseases. No one knows the exact mechanism that basically, makes someone prone to AD or FTD or DLBD. But like in each of the cases, we have different proteins. They get misfolded and they undergoes basically aggregation. Now, when proteins aggregate, they're like basically like let's say, sometimes you see mesh of hair clogging the shower drain. When you have this random mesh of hairs clogging the shower drain, water cannot go through. Now, it's those kind of cloggings is what happens when you have these proteins start misfolding and then aggregating. Now, in Alzheimer's disease, we have aggregation of beta amyloid protein and phospho-tau. In DLBD, we have basically synuclein. Now, synuclein aggregation also give rise to Parkinson disease. Uh, well, just so you know, the goal of today's presentation is not to bombard you with information, but just so that you can appreciate how different diseases are differentiated at the molecular level. And this frontotemporal dementia, this can happen from varieties of protein aggregation. In some patient, you have aggregation of this famous protein called TDP43. TDP43 aggregation is what you also see in ALS disease, which I'm sure all of you are aware of ALS. In ALS, you have aggregation of TDP43. In some FTD case, you also have aggregation of tau. So you can imagine, even if it's just one disease, it can come from misfolding and aggregation of 3 different proteins. And these are not the only 3. There are also more proteins, but these are just the famous ones. They were discovered basically in the early 20th century, like mid 20th century. So they are now very famous. All right, now that we know what sort of how different types of protein misfolding give rise to different diseases, you can imagine, since they're all dementia, it is important to be able to differentiate that which patient has AD and which patient has, let's say, FTD in this specific example. They didn't talk about DLBD, but that's a separate issue. But like they are trying to differentiate between AD and FTD. And the question is, why are they doing it? I mean, what's the fundamental reason why anyone would go through this painstaking process of figuring out a programming method to differentiate AD from FTD? Well, the reason is like people like, let's say, in the in some countries where, like, the medical facilities are way advanced, they can just directly do PET scanning. Now one like, something for my doctor friends, uh, like, we all recommend, like, do a CT scan, do an MRI, do a PET scan. It is also important for us to understand what's the fundamental behind PET scanning, what happens in the PET scanning, what happens in the CT scanning, what happens in MRI. Why do we see things like, the way we see things? It's important to also understand the fundamentals behind different types of diagnosis methods before we even recommend those diagnoses. Um, so in basically PET scanning, you have radio labeled proteins or small molecules. Like, let's say you have a protein that can bind to beta amyloid plaques. So you attach, so this molecule that can bind to beta amyloid plaques, you attach a radio label to that molecule. So when this molecule is injected into the human body, it basically goes and binds to all the beta amyloid plaques. So these protein aggregates. So if a patient has, let's say, FTD, he or she won't have any labeling with plaques. And then what happens in the radioactive, they start emitting, like, different radiation. Now for PET scanning, it's predominantly gamma radiation. And then you have sort of a scanner that detects in 3D, now where is the gamma radiation coming from. Now, of course, so PET scanning is an expensive technology because you have to have radio labeled molecule compounds and molecules. And so you have to, they are unstable, you have to stabilize it. The machine is expensive. Reading gamma radiation is definitely not something we can do at home. It's super expensive. The other technology is the more slightly crude way of doing things is called biomarker imaging. Like, sort of like, let's say we know from our experience of 40, 50 years, people who have AD, they also have, like, like, let's say, oligomeric beta amyloid in the bloodstream, for example. So they can take some blood, do some test, and then figure out, oh, hey, this patient may have Alzheimer's disease. So those are basically biomarker imaging. Now we can imagine, given that 10% of our elderly population have some sort of dementia, more than 10%, and this number is only increasing as a function of, like, time, partly because of, like, all this pollution and everything happening in the entire world. So this 10% is becoming 20% in as early as basically 20, 30 years. Now, when you have 1/5 of elderly population suffering, going through some sort of dementia, you cannot do this type of expensive technologies to diagnose, oh, hey, you have AD, or hey, you have FTD, or something like that. Which is why there is a need to sort of figure out a much more easier method to be done in primarily, as of now, in low income countries. And so as an example, so doctors from 5 different countries, from Latin American countries, they basically banded together, and from 11 clinical centers, they started collecting data from people suffering from AD and FTD, and also you always have to have healthy controls. You have to have healthy controls. So it's a fair distribution of numbers. So we have more AD, we have then FTD, you have more healthy individual. This is also consistent with what you expect, because Alzheimer's disease is the most prevalent cause of dementia, followed by FTD, followed by DLBD, which they did not do. Um, so quite like, likely why they have fewer patient in FTD than AD. And of course, they also have healthy controls. Um, they collected, so these are people, they already knew that they have suffering from AD or FTD, or they're perfectly healthy. And then the idea was, without doing all this complicated, like technologies and expensive, maintaining expensive machines, if they can sort of like figure out a way, sort of a machine, a protocol that can confidently tell you if a patient has AD or FTD. Now, if they are not doing this expensive definitive diagnosis, then how are they doing it? They're going back to basics. Like which regions are affected in each diseases. What they contribute to. So you sort of know if someone has, like, let's say, a combination of these problems, but not problems with AD. It is quite possible they may have FTD but not AD. So they're going by this sort of readout, which people can do just by talking to the patients, not doing anything intensive, like poking the brain or something, but basically just by interacting with patient, they can collect data about all these things through, like varieties of questions. Now, for example, like, let's say when some patient wakes up from, like, let's say coma or something, but like, let's say from paralysis, let's say, like from uh, anesthesia, people sometimes ask them, do you remember what day it is? It is this sort of questions, and they have, of course, a series of questions by which they judge uh, if any of, like these components are affected in this patient. So by studying these readout, they can sort of figure out, like if a patient has a AD or FTD without doing this complicated, expensive technologies. Yeah. But okay, now, so the question is, if someone can do all these things, why again go through all this trouble to figure out something called a machine learning algorithm? The whole point of machine learning is a very powerful technique. And machine learning is the science of 21st century. All right, now, like, let's say you all of you know Tesla have autopilot now, right? They just released the beta version of fully automated driving. How does the machine Tesla, like, of course, it has a core brain that decides everything. How does the machine knows, like, when to take a left turn, which one is a human, which one is a car, which vehicle is a bike, which vehicle is a truck? So the machine decides all these things before, like making a decision. Now let's say our brain is also a machine. Our brain is also a machine. When you are driving, how do we know that, like, oh, hey, there is a pedestrian walking, maybe I should slow down? How do we know? Because our eyes, we look at the pedestrian, we look at, like things that we see in front of our eyes. We see one head, one whole body, two hands, two legs, and it's walking. And from all those but distinct features, we know, oh, hey, maybe this thing is a human. So human life is precious. I should definitely slow down. See, now the brain as a machine takes into account all these parameters, our body features and everything, and then makes the informed decision. Now, if we can train a machine to look at, to basically observe if the thing standing in front of them have two eyes, one nose, one mouth, beautiful face, hair, body, hands, basically every single features that a human may or may not have. So that the machine can also process, just like our brain, oh, hey, this thing is a human. I should slow down. Same thing. How we know if it is a car or a truck? Because we look at other features. We know how a car looks like. We know how a truck looks like. How do we know how a car looks like? Because we have seen thousands of cars. We have seen thousands of humans. So we know how humans look like. Now, our brain as a machine is trained with by observing thousands of hundreds of thousands of human, hundreds of thousands of cars, hundreds of thousands of trucks, so that now at this point we look at something, we can confidently say, oh, hey, look, this thing is a truck, this thing is a car, and this thing is a human. Now same thing, a machine is trained just like our brain is trained. A machine is trained now, and the machine is exposed to 100,000 humans, 100,000 cars, 100,000 trucks. So the machine can also tell confidently if the next thing that comes in front of them is a car or a truck or a human. Now, this process is called machine learning. So you can imagine how powerful machine learning can be. Again, the goal of today's talk is not to teach you about machine learning, because as I said, we are not expert in everything. Like, let's say you are an expert in talking to patients, collecting data. Let's say I am an expert in machine learning, suppose, but I don't know how to collect data, suppose. So which is why people from two different backgrounds must collaborate and then exchange ideas. But of course, let's say you as a physician or doctors, if you don't know a thing about machine learning, how do you communicate with people from different backgrounds? So at minimum, what I believe is basically at least my friends from in the medical field, they have to know at least all the basics of different fields, so that at least they can communicate to people from different background and hopefully collaborate. Today's goal is just to introduce you to machine learning and how powerful it can be in the medical field. And I hope someday you will also use machine learning to do discoveries at tomorrow. Now, before we go into any basics of machine learning, let's first go through how important it is for any research to collect data. So, and you have to be very thorough when you collect data. So as we talked about, so they collected patients from 5 different countries, and you can see you have both AD, you have healthy controls, and you also have people suffering from frontotemporal dementia, and you have an equal distribution of males and females. You have varieties of age group, and then years of education. Uh, as you can imagine, let's say all this, the healthy controls are also elderly people of an average of 73 years of age. Now, it is important to pick healthy control from the similar age group. You cannot pick healthy control from like 20, 30 years of age and compare those people with elderly patient, which is why it is very important to pick your control samples carefully. In this case, the healthy controls are sort of in the same territory as the uh, patients, and they all have sort of similar level of education. Uh, Now, statistics is something we will not go into today. But this can take, hopefully someday, if we decide to teach you statistics in biology, maybe we'll discuss all these things. But this is called a chi-square test, and we do chi-square. You don't have to understand or know all these things. I'm just telling you all these things because they are in this paper. And people do chi-square test when we sort of work with percentages, vaguely. And these are basically called ANOVA. We have one-way ANOVA, two-way ANOVA, varieties of other things we won't go through. Uh, every time you work with data, you have to always ask the question, is this the best statistical tool that we can use? Because there are hundreds of statistical methods that you can use in every single case. Some of them are more appropriate than others. And then you have to also make a decision on, when you are working with data, if you should show the table, or maybe you should show a graph, because something visual makes more sense than looking at the data. If I were in their place, I would probably plot this data as a graph and not as tables, because numbers are difficult to look at. It's painful to the eyes. I always prefer graphs over tables, if it is possible. But regardless, and as we talked about in the beginning, instead of looking at the PET scanning or the biomarker imaging, they basically asked a bunch of questions to assess how capable they are in this skill set. Now, we will not go through these individual things, the memory, working memory, language. These are all we have to know is different countries. They have different set of questions to assess their different ability. Now, let's say these MMSE, MOCA, these strange looking names, these three are basically tests that deals with cognitive function. Similarly, we have other categories of strange looking names looking at different things. But more importantly, what you have to know is, how do you go from these questions to decide if a patient has AD or let's say FTD or something? Because every single answer is basically transformed into a number. Like, let's say if I ask you, can you tell me what day it is? If you are very confused, I'll give you a 0. Or like, if you know the rough date, but you cannot remember, if it is let's say 6th or 5th or 7th, I might give you a 2. So every single answer is basically transformed into a set of numbers. Now remember, numbers are easier to work with than questions. Now every single answers, they ask some 20, 40, hundreds of questions maybe in each section, and every single answer is transformed into a set of numbers. Numbers is something machine can analyze. Now, of course, but different countries, they have different rules and regulation. Some countries might follow this as MMSE, set of parameters. Some countries may follow ACE3 sort of questions. So different countries have different regulation. So different countries, like for example, this center, They did not evaluate patients on any of these scores. So they're all 0, 0, 0, 0, 0. They only evaluated patients based on this MMSE set of questions. Now, different countries, they have different, like, set of questions that they ask to people, and then they give them scores. All these scores and then transformed into, like, very complex table, which then machine can analyze. Now let's vaguely discuss what is a machine learning. Machine learning is basically you build a robot. A robot, you build a black box. You don't know how a robot thinks as like an outsider. As an outsider, you don't know how the robot is walking or talking or running and everything. You have all seen the robots from Boston Dynamics, right? You have the robotic dogs, they run through fields and everything. You don't know how they do that. So for you, it's a black box. So the machine learning is you build a black box, which normal people might not understand, which is okay, but at least they can get the answers they're looking for. So you build this black. Let's say I built a machine learning program to predict if I toss a coin, if I get head or tail. Okay. Let's say I build a machine to predict if, whatever comes out of the toss, if it is head or tail. Now there will be scenario when it comes out as head, and the machine says it's a head. Sometimes it will be a head and the machines might make a mistake. So you all have no machine is perfect. So sometimes the machine will predict the final output correctly, which is called a true positive. True positive means the value was positive and the machine predicted it as true. So the true positive. What is false positive? False positive means this the value was false, but the machine said it's positive. What is false negative? The value was false. The machine also said it's a false. What is true negative? Okay, you can guess. Okay. So what we do in machine learning, we collect this data from let's say these 5 different countries, and we then do varieties of statistical analysis, which we will not go through, to decide if healthy controls are different from AD and FTD and all these formalities. And then we have the very important step called feature scaling. What is feature scaling? Let's say you have a teacher and I have a teacher. Okay, we are in 2 different class, and we are in 2 different countries. You are from country A, I am from country B. Now in both the countries, you have both good students and also bad students in both the countries. Now let's say your teacher is too strict. Your teacher is not a nice guy. Out of 100, let's say in your country, uh, people who are good students, they get a score of 80 out of 100, whereas in my country, they got a score of 95 out of 100, the good students. Now I cannot tell, oh, hey, look, since this student got 80 out of 100, he's not a good student, but the good student got 95, he's a good student. No, that is not correct. So which is why those data has to be normalized, which means a score of 80 in your country is the same thing as score of 95 in my country. Now that is called feature scaling. They're dealing with 5 different countries. Now people who are giving the scores, sometimes they are too harsh. Now when you compare the healthy controls, you know that they all are supposed to be the same thing. Now that is how you scale all the features that they're collecting on. And then you do more statistical garbage. You build a machine learning pipeline, you do varieties of other things, and then you finally classify, oh, hey, look, so these patients are your healthy controls, and these patients are your AD or FTD. And then you evaluate how many AD patients are in the FTD group, how many FTD patients are in the AD group, and how many AD and the AD groups, all basically the true positive, false positive, all those things. Okay, now, and then we evaluate, like, how many AD in AD group, which is this group, how many FTD in FTD group. Now, what this table means is 90% of AD patient, which were definitely basically had AD, the machine also said they had AD. 67% of FTD patients who had FTD, the machine said they also had FTD. Now, these two numbers, this is what the machine predicted, did not predict correctly. So 33 patients that definitely had AD, sorry. They definitely had FTD. The machine said they have AD. So of course, this is where this model failed. This is called a confusion matrix, just so you know. And then you have a table, it's called ROI AUC curve. This basically tells you how good your model is, how good your programming is to predict if a patient is AD or FTD. Now, let's say if I toss a coin, okay? If I toss a coin, and then if the coin is positive, the machine says positive. If the coin is negative, the machine also says positive. Then it is not a good machine, right? Then the way the machine is predicting is not accurate, right? So we will not go into details. We plot basically sensitivity as a function of 1 minute specificity, and sort of like, specificity is the rate of false positive divided by true negative and false positive. These ratios will look very confusing to many of you, maybe all of you. But don't worry about this ratio. All you have to worry about is this line. What is this line and what is this line? As you can imagine, this is the y-axis sensitivity and the x is 1 minute specificity. So what is the slope? The slope is y over x. So what is y over x? If you divide this by this, you end up with true positive over false positive. So it's true positive divided by false positive is this line. Now, of course, in this case, the slope is 1. It means the true positive is the same thing as false positive. What it means is if I toss a coin and the coin is head, the machine says it's positive, and the coin is tail, the machine also says it's positive. So the machine cannot distinguish between head and tail. Of course, this TP by FP becomes 1, and this slope is 1. So this line suggests it's basically is not a good model. It's not a model at all. So your job is to end up with a model that is very, like, far from this line. Now, what it means is the true positive has to be much higher than the false positive. Now, you can say this line is sort of false positive, this line is true positive. At every single point, this point has to be higher than this point. So the true positive has to be higher than false positive at every single point. As long as the model is very far from this central line, it's a good model. As long as you understand this, and then you collaborate with someone who is from machine learning background, and then they'll show you, hey, look, this is what I got. At least you can understand what this graph means. As long as you understand that, That's all the machine learning you have to know. Now, this is a very like, in the next 10, 20 years, the entire medical field is transforming into machine learning. So it's best you understand what, like, confusion matrix look like, what the ROI AUC curve look like, what they means. Uh, in basically 20, 25 years, the machines will diagnose everything. My guess, machine will also do surgery, which they are doing right now. The machines will do diagnosis. The machines will prescribe medicine. The machines will do everything. When the entire world is transforming into a world of machines, it is important for us to understand if what the machine is doing, if it is right or wrong. As long as you understand today, I think it's enough. Hopefully, like, you will learn more about, like, machine learning. And the whole point of machine learning is differential diagnosis, I would say, in the medical field right now, at least important in this lesson. You can also, like, think of varieties of projects in varieties of things in your, like, let's say, the environment. And you can also apply machine learning to predict, like, let's say, if a patient has, like, dengue fever, or maybe a regular fever, like things like that. If a patient has, let's say, measles versus something else, like, let's say, when you have measles, you have this red spots, like, popping all over your skin. Now, as a doctor, we know how to figure out if this spot is a measles or not. Now, if you can train a machine to analyze the spot, you know how our eyes perceive a measles spot. We look at maybe the size of the spot, maybe the elevation of the spot, how red is at the center, how the color is diffusing as a function of radius. The way our eyes are analyzing the measles spot, if you can program a machine to do all those things, well, tomorrow the machines are diagnosing measles. So this is how the entire world will transform into a world where machines do all the medical jobs pretty much. And then, of course, we have to figure out, like, how important, like, how accurate is the machine, like, in the prediction compared to the true prediction. We want to go through basically individual plot. That is not the point. But all you have to know is this thing called n feature. What's a feature? Feature is these parameters. You can remember this mini ACA, IFS, and NPI from these table. Now, what the machine basically found out, now based on this mini ACA, IFS, and NPI score, only based on these three score, a machine can predict, along with age and years of education and sex. The machine can successfully predict if a patient is healthy, or if it has AD, or if it has FTD. Now, this is what the machine does. Now, remember, as human, as individual, our brain is limited. We look at all these numbers, all these categories of, classification and their evaluation, and it is impossible for, any layman like you or me to conclude if we can predict, Alzheimer or FTD based on this Barthel score or Pfeiffer score. It's impossible, but a machine can analyze thousands of data in a fraction of a second. The machine basically figures out all the other parameters are not relevant. They're relevant, but they're not needed to predict, if a patient has specific disease or not. And the machine also tells you how important are the parameters. If you add all these numbers, like let's say if you had 0.25 plus 0.16, 15.12, they all come out to be 1. So it means this mini ACA score has a 24% probability, has a 24% contribution towards figuring out if a patient has AD, FTD, or healthy. Similarly, sex, if you are male or female, has a 5% role to figure out if you have AD, FTD, or healthy. Well, this sounds surprising. How come sex has a role? I can tell you it is known that females are twice more likely to undergo dementia above the age of 65 than males. So you can imagine sex is bound to have a role. But if you did not have a machine, you cannot predict. The role of sex is only 5% or maybe 5.5%. That the machine analyzed all these parameters and how effectively they contribute towards the final diagnosis. And as it turns out, sex does play a role. Now, the years of education does play a role. How? How does years of education play a role? Because if you are educated, you know, I should not do this. I should avoid eating this type of food. I should avoid, like, going into polluted areas, because if you have more pollution, if you are exposed to more garbage, the garbage can really mess up the brain. So the years of education does have a role. It might not be significant, it's only 11% or 12%, but it does have a role. Now, age, definitely age have a role. We all know that if someone is 60 versus 80, the patient with 80 age is more likely to have some sort of dementia than a patient of 60 plus age. So all these parameters, they have a role, and the machine also tells you what is their contribution towards the final diagnosis. So the machine has sort of basically a formula, and now I'll tell you how this robot works. What this robot or this machine does, it comes up with an equation involving all these parameters. Let's say I'm just talking garbage, but just to give an idea, let's say a machine tells you if 2 times mini ACA plus 4 times IFS minus 2 times MMSEA plus 0.5 times age plus 0.05 times sex plus 2.5 times years of education, if this final number is more than, let's say, 215, a patient has AD. You see what I mean? So the machine comes up with an equation involving all these parameters. And if this calculation is above or below certain range, the machine predicts if it has Alzheimer or FTD or healthy individual. I think we pretty much covered this project. I am hoping at least today you learned about what a machine learning is and how you can use machine learning in medical settings, how it has been used. Remember, every single work and research involving machine learning and medical field is bound to go into very high impact journals like Lancet or NJEM. Any research involving machine learning and medical field is bound to go into high impact journal. So I strongly encourage everyone to figure out how they can use machine learning in their environment, and then sort of make a step forward and replace humans with machines. Exactly. But more than that, I must tell everyone, my friends from medical field in India, they're basically sitting on a gold mine. Because as I just told you, India is very complex in diversity and everything. So you have more like types of disease and everything than what you may find people like diseases in like let's say US or UK or something. You have more complex disease. You might find an individual, also partly because the population, you are more likely to find an individual, someone with like let's say the dengue and COVID and something, and that's a complex disease, right? It's not simple. You might not find someone who has dengue and COVID and A and B in the US, but you are more likely to find those individuals in India. So you can imagine, I would say, how important and how easy, how relatively easy it is to publish high impact work. And but more than that, those information will be used by people across the world. Now, going back to the question, why should the doctors do research? And the correct answer is, I would say, when doctors make a diagnosis, let's say you as a doctor, you are diagnosing like let's say a patient with just randomly diabetes with something. Well, the patient leaves, right? And then you are seeing another patient. Now, no one in the entire world knows what you did. People die, you will die, I will die, we will all die, but these publications, they will be there for life. People like after 200 years might look at, oh hey, look, this guy from this country published this work in 2022, and this work is beautiful. uh, and Another reason why doctors should publish, it basically goes back to the same concept as a patent. Let's say uh, two people, okay, two people, and they both make the same discovery. Let's say you also diagnosed someone with the dengue, with COVID, with some weird disease, and let's say someone from like let's say Peru, another country, just come up with this number name here, also diagnosed someone with dengue plus COVID plus the same disease. Now, the other guy published a paper and you did not. Now, what that means is when people like, after 200 years tried to, wanted to look at, oh, hey, look, who was the one who discovered for the first time that like, humans can have both dengue with COVID and this disease, and made the first discovery. They won't know you. They will know the guy from Peru who documented everything and published the data. Now, I would say when you publish, this becomes your legacy. You will die, but your work will live forever. And this is the only reason why we all should publish. Now, of course, we should publish, that's a philosophical story, but we should also know the what sort of work we have to do to publish. And I hope the goal of this journal club will sort of like maybe tell you different types of research that can be done in the field of medicine, and hopefully you can also publish, we all can publish high impact journals. Now that we have sort of like we sort of went through this massive Lancet paper, you may remember is we also uh, also sent you like some very four fun papers. Now this is something my physician friend can do right away. These are all published in NJEM, very high impact journal. Like let's say here in this case, two doctors, they may or may not have collaborated, I don't know, but they must have. They found an individual who basically had pockets of gas. And this was unusual. And well, it is quite possible many of you, at least some of you, or maybe one of you may have encountered this sort of weird case in your scenario, but you did not publish. So people don't know your name, but they will know this name for the rest of the humanity. Well, so my point of sending these 4 papers is these are all weird cases. Now, in this case, he had pockets of gas, and the important thing to consider is how critical it is to document everything. If you see a patient and then not document everything for your own record, you cannot publish. You need data to publish. Here, since you're all exposed to, you all encounter 50, hundreds or 500s of patients every week, you are bound to encounter individual with interesting case. And you can always publish those cases, but it's important to collect in-depth data. His history, his medicine that he or she was treated with, blood pressure, everything, all this test that they did, diagnosis, everything. And then you have to have some beautiful, convincing images. Now remember, this is NJEM. It's a very high impact journal. I don't expect you to publish in NJEM tomorrow. Publishing in this high impact journal will take time. It will take expertise, experience, everything. But at least there are a lot of journals they are not this high impact, but at least it'll get you started with the journey. Another story, it's a very interesting story. It was a diabetes patient, and they did not expect, but basically he had blood pooling in his eye. So a convincing figure, a convincing sort of analysis, and then a ton of documentation is something you should do from now on. And hopefully someday, maybe tomorrow, maybe after 7 days, maybe after a week, you will encounter very curious case. It might not be this curious, but it will be curious enough to publish. Here, again, the patient had dysphagia, but from an entirely different reason, which is not common, which is not normally seen. And then here, the patient had sort of dark spots growing on the left palm, and then they did a hematoxylin and eosin staining, and then they found nucleus and cytosol of the fungus and bacteria and everything. So they published it. The point is, you can imagine you all have seen cases like this in India and maybe in other countries. But if you don't publish it, people will never know your name. Now, on paper, these were the guys who, for the first time, published a case like this. So it is important for basically all of you, it's important for everyone to document every single thing. And hopefully someday you will find curiosity cases of your own. And even if you can publish in NJEM, you can at least publish in good enough journal, and hopefully that will be your legacy. With this, I would basically stop, and let's see if you have any questions.
Thank you, Dr. Parasar. it was amazing to learn about machine learning, the new cutting edge technology. So if you have any other questions, please go ahead so that we can wrap it up. Okay, let's start from Devansi.
Hi, it was really fun learning about this. It was really great experience to learn about this. I just had like a question, like as in like, would you say like when you were younger or something, was there any certain person that really like influenced you on this journey, like the certain medical journey?
Influence?
Yeah, what she's trying to ask is how did you get influenced to do all of this research work, and how did you get started and all of this? Is it, am I correct?
Yeah. Yeah.
Okay.
Yeah, I
So
mean,
that's what.
it's definitely is a long journey. Well, I never thought about it like, from your perspective, but I definitely understand the questions is, I would say no knowledge is useless. If you are thinking like, let's say, oh, hey, look, I'm not interested in physics does not excite me, then you are wrong. Because you will use physics in the future, even if you go into medical field. Um, um, I would say, like, my background was primarily mathematics in the beginning, statistics, mathematics. Then I switched to physics. Then I switched to chemistry, and then I switched to biology. And right now, I work mostly with neurodegeneration, and I develop technologies for other people to use. So, and then sometime in like 7 years back, I was building softwares. So I would definitely say, like, know every single knowledge will be useful at some point in your life. But definitely learn, like, whatever, like, you have, use all of your resources wisely. Take all the advantages that, like, you are offered, and always have this sense of curiosity in you. And trust me, you can find research problems around you with um, in your settings. Does that answer the question? I'm not sure.
No, yeah.
I had a very complicated journey. It was not like, simple.
No,
No,
yeah.
that's amazing. Actually, what we are learning, like knowledge is precious. That's first thing we are learning. Like it's you have to keep your eyes and ears open all the time. And second thing, don't let your curiosity die under any circumstances, right? So you just document everything. You just write everything. You never know what might come across. What might life might lead you to something else to find something. So just document everything, be curious about everything, and try to grasp knowledge, try to understand whatever excites you. So that's I think that's how Dr. Parasar must have get into this thing, and at least that's true for me. Like I was curious about science, I'm curious about biotechnology. That's how I get into all of this. So I think does that answer you, Sona?
Yeah, it does. Thank you so much for sharing with us.
Okay, anyone else? Vaishnavi?
Hi, my only doubt is that I'm currently doing a rotation, like an observership, but then I don't know how to. I started a case report, but then the patient left. So how do I make sure that I have the data even after that? Like, I can't take any screenshots because it's against HIPAA violation. So I'm confused as to how to complete that report.
Well, I mean, definitely you cannot. I mean, those things will always be there. The patient has to agree to give you all of their data. Those things will happen to you. Well, that's the way of life. We just move on.
Let's say this, like these are the limitations of research work. Like those are unpredictable. Sometimes those patients will agree, then they sign those consent forms and all, but then half of the way they will leave. So those are the limitations. So you cannot do anything about it. I mean, sometimes what I do, I connect with them personally. I try to find out. I mean, without invading their personal space, I would try to find out if is there anything else we can do as researcher, if we can help them or anything. So everything have to be under that guidance and whatever IRB rules and all, but you have to respect their privacy as well. So it's always what my mentor suggests me, like it's time sensitive, you cannot take them for granted. If you find something, go ahead and quickly finish that stuff off. I mean, otherwise they are very unpredictable because they are not associated with the clinical thing unless you are paying them and all. So it's a limitation. If somebody is gone, it's gone, he is gone. So whatever data you have left with, continue with that and try to find someone else.
Oh, okay. So you mean to say that I have to complete the case report within the duration of the hospital stay of the patient?
Ideally, unless you get that person to communicate with you and come back and do some more projects. Otherwise you can't force them. That's the thing. Patient
Okay.
comes first.
Let me just tell you something which is not right, but that's how it has been. That's how it will always be. Now, for example, let's say you are let's say having pasta. Okay. You want to go to a restaurant and then try some pasta. You go to let's say a small scale restaurant. They serve you pasta that looks like just a random glob of something, some random garbage glob of something, and you might pay $10 for it. And let's say you go to a 5-star restaurant, they decorate the pasta in a way it's like a piece of art, and you might have to pay $50 for it. Now that is also the story with publishing. If you can properly present your data, even if you don't have enough, you can always publish it somewhere. But of course, if you, well, that's how it has been. You see all those high-end journals, they have beautiful figures. The data has been analyzed perfectly. Everything has been documented. In my opinion, if you think you have some data, if it is, even if it is not a complete story, you did not get to the ending, you will not publish in Lancet for sure. You can definitely publish it somewhere. But of course, to compensate for the missing information, well, like I said, this is how it has been, which is not right. But if you can compensate it with nice figures, nice statistics, analysis, basically squeeze the last drop out of that lemon. And you may still be able to publish somewhere. Like it might not be a high-end journal, but definitely somewhere.
Oh, I didn't know that we can publish a case report even without completing, like without the complete information.
Like I said, it all also depends on where you want to publish. It will
Oh,
not go into a high impact journal, but then there are also but you have to be careful. Like for example, let me share my screen. You have to be, you cannot just publish anywhere you want.
See, there is a risk of acceptance too. Like you can send to multiple journals. It all depends what excites them, how authentic they think of that data. So
There's
you just
something Yeah, please.
Yeah, so you just have to keep on trying and keep on sending, see whoever accepts, even if it's something you think there is scope of more research. Okay, so never get disappointed, just keep on trying and send. Okay, go ahead.
This list is called Bale's list of predatory journals. You cannot publish in any of these journals. Make sure you check, your journal is not in this list. Like for example, you will have even some medical journals. There's 22, at least 22, with the word medi. You cannot publish in these journals at any cost. So you have to be also careful where you want to publish.
You mean to say that these journals require a complete case report to publish?
No, so these journals, they don't require anything.
Oh, sorry. Okay.
You can just say, oh, hey, look, I am 5'8". They will publish it. Okay, look, this guy is 5'8".
Oh,
So
okay.
basically,
Thanks.
they don't have any standard. They
Uh-huh.
don't review the work. So these are basically sort of your blacklisted journals.
Oh, okay.
So you should check this list and make sure, you don't publish in any of these journals.
Oh, okay. Are there any journals which are easy to publish and that are free?
There are definitely, ma'am said, you always strive from a high impact where you think your work might get into. Of course, if the work is not fully complete, right? If you think the things that you have done is still novel enough in its own capacity, you can try to compensate the data with so you cannot have incomplete data but also garbage writing, ugly looking figures and wrong statistics, right?
Hmm.
You have to compensate let's say 80% data with high level of statistics, high quality figures, high quality writing. And maybe because people who make all the decision, they're also human, right? They make mistake, they might overlook the fact that, oh, hey, look, there's it's missing some data, maybe it's okay.
Oh. Hmm.
Because humans right now, fortunately, machines are not deciding, making all the decision. So at least
Okay. I see.
yeah.
And there was another case, but it was not diagnosed. It's still under progress. I mean, it's a difficult case. No one was able to actually diagnose it, the cause of the hypokalemia. So, can
Oh,
I publish that thing, or should I wait until it's actually completely diagnosed,
well,
or is
you
it
just
not
saw,
possible?
right? As long as you have some preliminary diagnosis, it's always the first one to publish is the first one people remember.
Uh-huh.
So sometimes this is always the case. Like, let's say I find some very exciting piece of data, but if I try to complete the story, it might take another, let's say 6 months, or maybe 2 years or something. And I
Mhm.
am scared, what if someone else publishes it before me? So what I
Mhm.
do, I take what I have basically a story that makes sense. It might not be complete. Like, you might not know what's the molecular cause of the disease, but as
Uh-huh.
long as you have some minor evidence, I would say publish it first. If you
Oh,
are
okay.
scared it's unique enough, but not unique enough that someone else might also encounter a case like this, it's important for you to publish something. Even doesn't have to be a very high impact journal. Like, as long
Mhm.
as, wait, now then comes to the question of what's a good journal, right?
Oh.
But let's say we talked about this thing called impact factor, I think last time, right? And today we talked about two teachers in two different countries grading differently, right?
Mhm.
In let's say your country, someone gives 80 out of 100 to a good student. In my country, we get 97, for example, right? That's the story with journals in physics, chemistry, biology, medicine. Physics journal, they tend to have like, low impact in general. Like, the best journal is called PRL. It has an impact factor of 10 or something. 10. That's
Oh,
the best journal.
wow.
So you cannot say, oh, hey, look, just because PRL is 10, but Lancet is 200, the PRL is 20 times worse than Lancet. No,
Uh-huh.
you have to normalize, right?
I see.
Everything. Like, for example, in biology, the best ones are called CNS, Cell Nature Science. They are like around 75 now.
Mhm.
So 75 in biology is equivalent to, like, let's say, like, 200 in medicine, is
Oh,
equivalent to 10 in physics, is equivalent to 20 in chemistry. See what I'm trying to say?
yeah.
So
So the
like
impact factor
in
is different for, I mean, there's
different
a
field,
curve for the impact factor in
different
different
field,
fields as well.
definitely. You cannot, like, that's called normalization.
Hmm.
So like, let's say, like, we don't publish anything if it has less than impact factor of, like, 10 or something in biology. Like, we don't want to publish there. We
Hmm.
always target for anything more than 15
Okay.
in biology, which is considered like, good journal.
Okay.
Um, so the same thing, and an average journal should have an impact factor of 5 or something. I would say if it less than 5, it's not been worth publishing. Like, you can have, like, a volume of 200 papers, but it might not mean anything if it is
Mhm.
not recognized by other people in the field.
I see. Okay.
See, journals are they are like, magazine. You can have your own journal tomorrow. It's very legal.
Oh.
You can say, like, okay, look, from tomorrow I will start my own journal. You can do that,
Oh.
but it's not recognized by other people. People don't know your journal yet.
Okay.
So you can publish anywhere you want. Hopefully not anything from this list, but anywhere you
Hmm.
want. But if people don't know that journal, you won't get noticed. It will
I see.
definitely add to the volume. And right now, if you are interested in volume, then go for it, because we all have to start from somewhere.
Mm-hmm.
We cannot publish in Lancet overnight, right? It's
Yeah.
not possible. So right now, definitely shoot for volume, and at least learn how to do research. And hopefully in due course, you will encounter curious case of Benjamin Button or something, or maybe someone like Pa or something, and then publish in a good journal. And trust me, you keep trying, you keep documenting everything, you are bound to find something interesting very soon. And that is only for case report,
Hmm.
right? Which is
Hmm.
which we discussed towards the end. In the beginning, that's not a case report. That's a research.
That's a research.
And that you can do anytime you want. No one is stopping you. Well, you don't have to collect your own data. You can find data basically, like, publicly available databases.
Mm-hmm.
So if you want to do research, you can do it like today.
Mm-hmm.
You just have to know how to do it, which is what I think is the main goal of the journal club, is to teach you
Okay.
the different types of research you can do potentially in the field of medicine. And hopefully you can pick out something on your own and then just go ahead
Okay.
and collaborate on everything, and then just hopefully find something interesting.
Okay. Thank you.
Okay, those are nice set of question, nice set of discussion points. Swada, do you have anything? Swada, are you there?
Yeah, I
Okay.
don't really have any questions.
Okay, let's go to Ayan then.
Yeah, I don't have questions either.
Okay, so next time, so the next session, which is going to be next Sunday, it's going to be on liver tumor and oral cancer, which is my subject. I will present that. So make sure you all take notes and take point. I would encourage more questions. I want to answer what curiosity do you have. Otherwise, it's worthless to just talk and let all of these things out there and there is no conversation. Okay, so everyone, I will encourage heavily, go ahead and press your curiosity button and ask as much question as possible. Okay, that's encouraging for us, so that we will know what kind of sessions we should conduct, how we should say, and what excites you. Okay. Okay, so I guess no one else has any other questions. Let's wrap it up. I'll see you next Sunday. Okay. Thank you all for joining.
Thank you.
Thank
Okay.
you.
Thank you so much,
Bye.
everyone.
Thank you.
Thank you, ma'am. Thank you so much.